All right. Okay. What you'll realize is the number of carbons over here will match the moles of carbon dioxide. If it's like a 4 over here, you should know that there will be a 4 over here. And if you want to balance this particular equation out, you realize that you need to balance the number of hydrogens. There are 4 over here, so you want 4 over here. Now you have a total of 4 oxygen atoms, so you want 2 over here to balance that out. Okay. Now this is for complete combustion. When you have excess of oxygen, sometimes what can happen is you don't have excess oxygen. It could end up taking less oxygen, which means incomplete combustion. So instead of carbon dioxide, carbon monoxide is produced. Now I went off on a slight monologue about how to balance it out. Let's balance this out, then I'll talk. And I think this is going to be 1.5, right? I have 3 oxygen, 1 over here and 2 over here. So that's a total of 3. And if I put 1.5 over here, that should make this number 3. But I can't put a 3 over here. What I'll do is I'll multiply the entire equation by 2. So what I'll get over here is 2, 3, 2, and 4. And now you'll see that the equation is pretty balanced, right? Everyone gets this? Right? Thumbs up, thumbs down. Everyone gets this? Kira? Pretty easy, nothing special. Everyone understands why I multiplied the equation by 2, just to balance it out? Yeah, okay. Achha, this could happen with anything, right? So let's see if we can balance out a more complicated looking equation. So I'll put an alcohol over here. Let's say we have propanol, which is C3H, I think 7OH, reacting with oxygen to produce carbon dioxide and water. Let's balance it out. So this seems very challenging for most people, and they ask this a lot. So a general rule is you only have to worry about oxygen essentially. How many carbons do you have? You have 3. So that means you'll produce 3 carbon dioxide molecules, because all the carbon from here is going over here. You have 8 hydrogens. So over here you should put up 4 to get 8. Now you realize that I have 6 oxygens over here and 4 over here, or a total of 10. You also need 10 over here, but you realize there's 1 over here, and the other 9 will go over here, right? This will contribute to the other 9 atoms. How do you get 9? Well, I'll put a 4.5 over here, and that'll make me very happy. 4.5 like that. Now, most of you will realize I can't really put a decimal over there. So I'll multiply the entire equation by 2 now. 2 over here. 4.5 times 2 is 9. This is 6. This is 8. Yeah. Thumbs up, thumbs down. Why is this keep? Yeah, everyone gets it. I need this. I can't hear you properly. Can you be a little louder?
Can you check WhatsApp for a minute?
Sure. Yeah, ठीक है. Yeah, looks okay. No, it's not okay. No? Combustion 2. Why did you write O3 on the right hand side? I don't know. It says O300 carbon. But it looks okay. Looks good. No, it's
What's
2,
like the
2.
first one is combustion. Usha, it's incomplete. What's that?
Yeah, it's 2 over here and 2 over here. Right?
Yeah. The incomplete one is equation क्या है?
I can't hear you, Asa. Why is your audio so low?
Sir,
Why-
ये incomplete वाला मुझे समझ नहीं आया.
Incomplete wala is just carbon monoxide being produced. Does that make sense? If carbon monoxide is being produced, then you can balance it out. Yeah?
The first equation is different and the second is different.
Yeah, so essentially what's happening is in the second equation, carbon monoxide will be produced. Once you know that, you just have to balance the number of oxygens later. But if it's incomplete, instead of carbon dioxide, carbon monoxide is being produced. That's the point.
Okay.
Does that make sense?
Yes.
Yeah, simple as that. Okay, shall we move on? We can practice a little later, I think, but like a general idea on it. Yeah, alcohols will be the most trickiest if you guys can do this. It's pretty good. Oh my God. Should find a different way. Do you guys hear it beeping when someone else joins, or is it only me who can hear it? Everyone can? Yeah, I don't think I can turn it off because I want to control who's coming in, who's not. If someone starts, badtamizi, so I'll not invite them again. Chlorine in sunlight. Another name for this reaction is substitution. This is your first official reaction for an alkane. So here's your alkane. We'll use methane as an example again, which can react with chlorine. Okay. And you can write the chemical formula for this. I'm trying to show the process, so I'm showing all the bonds. This will give you this thing. Okay. Now, this reaction requires the presence of, this can happen at any temperature, no conditions required. This happen in the presence of UV light, or in other words, sunlight. Okay. Is it mandatory to multiply it by 2 for balancing? In A levels, they don't care about if you answer it in decimals. So my best guess is like, you don't have to multiply it. Okay, it's not even a guess. I think like if you write something that's correct, it's fine. But in O levels, they just prefer you guys to have whole numbers in your answer. So you don't have to multiply at the end of the day. But if you think it's, maybe the second question is about moles. And if you think decimals will confuse you, convert it into O levels. Otherwise, you don't have to. Okay. Now, what's interesting is chlorine looks for this carbon-hydrogen bond and replaces the hydrogen, right? You see this is happening. Chlorine ends up replacing this, and hydrogen ends up replacing the position for chlorine. So they're substituting their places, and it's called a substitution reaction. What could happen is it can't really stop there, because let's say another chlorine molecule is present in the solution. एक atom तो नहीं होंगे ना, एक molecule तो दोनों के नहीं होंगे. If another chlorine is present, is right next to it, let's say over here, it can easily attack this hydrogen, right? So this can also replace. So what could happen is this could have multiple products. What kind of products? Well, the first product is drawn for you, which is CH3Cl, but it could make all of these products. What does this mean? Well, either you could have one chlorine attached, either you could have two chlorines attached, either you could have 3 chlorine, 4 chlorine. All of them are possible results. And if you leave this reaction going with plenty of chlorine long enough, what's going to happen is the chances of getting all of this turning into CCl4 will increase. So you can do that, but generally when you're doing it, there's no control. So in one solution, you'll have like, or like one reaction, one batch, you'll have like all of these molecules present, some in little quantity, some in more quantity. Does that make sense to people? Thumbs up, thumbs down? Pretty straightforward, I think. A lot of people get it. No one seems to not get it. All right. So believe it or not, we're done with alkanes. This is all the reactions for alkanes. They can combust. They can undergo substitution. They don't undergo any other reaction. So here's a term which people might find very confusing, which is alkenes are unreactive. And people are like, that doesn't, sorry, I'm saying alkenes, I meant alkanes. But people will be like, that doesn't seem right, because alkanes, what are they? Well, some alkanes you already know are natural gas. Petrol, diesel, all your fossil fuels are alkanes essentially. So it doesn't make sense to call alkanes unreactive, yet the examiner and your book will call them unreactive. Can anyone tell me why? Kaval, yes, to get CCl4, you'll need 4 molecules of chlorine. Roa saying saturated. Alina, you're asking, explain again which part. Can you be a little more detailed? I'll go back to it. Right now, I'm asking, alkanes are unreactive. Okay, why do you think people like to call them unreactive? Because it's like, so if that's a question in your head and you can answer multiple ways, the correct answer is, or the way to think about it is, aside from burning, they don't do anything else. They'll burn and they don't do anything else. So think about it this way. What is burning? Reacting with oxygen, right? If there was no oxygen in the atmosphere, this would do absolutely nothing, because it's very sensitive to oxygen. But if oxygen is not present, it'll be just padawa. It won't do anything, right? Like it'll absolutely do nothing. So that's why alkanes are considered extremely unreactive. Another point is that they've been around for millions of years underground and they survived without any reactions. They're pretty inert, right? Yeah, I hope that made sense why they're inert. Any questions related to this before I move on? The understanding should be that alkanes generally are like incredibly inert. Sure, they can combust and we use them for that a lot, but other than that, They don't do any other reaction. And their only burn really well is they just have a, let's say, an allergy to oxygen. Other than that, not an issue. Shall I move on? I said so, unreactive if not combusted. Last part about chlorine and hydrogen bond. I still don't understand which part I should explain. Like a little more detail would help. I can go back to it once I know what you're talking about. Tigo, what do you mean the last bond? I don't know. Just be a little more like write a small paragraph down. For now, we'll move on to alkenes. All right, alkenes, you probably know them as your unsaturated hydrocarbons. Saturated hydrocarbons. Why are they called that? Because they can absorb more hydrogen because of their presence of a double bond. Okay. Here is one reaction, which is reduction. Of an alkene. I shall draw an alkene for you guys. Yeah. What do you need for this reaction? Is heat, pressure. High heat, high pressure. I think it's at 200 degrees Celsius, if I remember correctly. And nickel as a catalyst. Your first reaction of an alkene. Isn't this an addition reaction? Yeah. Yes. Yeah. The reason for why it's called an addition reaction is an addition reaction by definition is A plus B gives you C. A new product, but one product. So essentially what's happening is two things are joining together to form one thing. There's no byproduct like plus H2O or anything like that, not there. So technically this is an addition reaction, but you can have addition reaction and something else going on. So this is more popularly known as a redox or reduction reaction because the alkene in question is being reduced. Why is it being reduced? Because there's a gain of hydrogen. If they ask you, describe this, what is the name of this reaction? To call it addition reaction would be less accurate. It would be more accurate because you're correctly describing exactly what's going on. So it's not an addition reaction, it is a reduction reaction. Does this make sense? So alkene is basically becoming an alkene. You are correct. Okay. This is a very important reaction because if you ever want an alkene and you have too much alkene, you do this. And if you have an alkane And if you want an alkene, there's a pretty clever way of doing it, but we don't study it. It's essentially first you turn the alkene into a chlorocarbon. Yeah, my video is glitching. It's really glitching. Yeah. All right. Can everyone hear me? Just thumbs up if you guys can hear me, because I think the video is gone. Yeah, I think we're good. But the video is gone. Oh well. Okay. Reduction. Let's do the second one. This might be a slightly longer class. I really keep the second is hydration. All right, gotta close WhatsApp now. I'm giving H2O some colors so we can track what's going on. Yeah. Now the conditions for this reaction, they asked like no tomorrow. What are the conditions? The temperature required is 300 degrees Celsius at a pressure of 60 atmospheres. That doesn't look like 60, so I'll rewrite it. And the catalyst used is phosphoric acid. Does that make sense? Yeah, so essentially you ended up getting an alcohol. Pretty cool. Now I'll tell you how important this is. The part where you have to kind of really focus on memorizing this part, because they ask this like no tomorrow. Let me show you the marking scheme. A copy of the marking scheme here. So they asked, what is the condition required for an alkene to turn into an alcohol? They gave some chemical equation and they asked, what is it, right? And essentially you realize that they really want you to know these conditions. So at one point, they wanted you to answer these points, any one of them for 1 mark. I think they were asking just one of the conditions. At another point, you had to quote all of them, or like not all of them, I guess 2 of them. But yeah, they really like asking this. So if any condition you want to know, this is the one. It's also the most unique one, so you don't get confused very easily. I personally hate it. So yeah. Okay, let's move on. Okay. Number 3, another reaction. Polymerization. with a twist, addition. So you could, essentially what ends up happening is can polymerize, which is kind of like this blue thing. Like that. Okay, and this chain could be, 4 carbons long, 8 carbons, 20, 80, 200, 1,000, 10,000. Doesn't matter. It literally matters how long you keep it cooking, essentially, how long the reaction is, and it'll keep on growing. And yeah. Why is there a pixel on my screen? There's no conditions for this, so we're good. But there is a naming convention. So let's say you have ethene. This is ethene on the left-hand side. This is the monomer for the 2B polymer that is formed. Monomer. This is the polymer. So the mer probably just means like a molecule, another word for molecule. And mono means one, poly means multiple. I think people know that. So monomer and a polymer, right? What would you call this? The name essentially for this polymer comes from this itself. So you just call it polyethene. Polyethene. So have you heard of polythene bags? You take ethene gas, polymerize it, and you end up making plastic. Right? Does this make sense? Yeah. If I do this, I'm trying to turn on my video still. It won't let me. I think it's just, what I probably can do is restart Zoom. Which probably won't happen. So here's a question. If people get it, let's say I have a molecule like this. How will you show the polymer for it? Now you got to realize a few things. The molecule in real life is not in a straight line. We discussed that in isomers, right? So it's not in a straight line. So what you do is you try to redraw it in a way where it is really friendly. I think I made a mistake. There's one extra hydrogen over here. I think it's fine now. Yeah. So you want to redraw this entire molecule in a way where you can actually draw the polymer out of it. What do I mean by that? It just makes your life easier if you redraw this like this. Essentially condense this entire part out. So let me do that. like that. Keep adding carbon in the direction what's being provided. Essentially, the idea is a little more simpler than that, which is that what you have to notice is essentially this molecule breaks up, the double bond breaks open, and each carbon now can create a bond from here and here. So you draw those bonds out like so. And this is what you call is a repeat unit. Right? Why is it called a repeat unit? Because you essentially end up repeating this to draw your polymer. Does that make sense? I'm just copying it. And this is my repeat unit. Or like the original part was my repeat unit. Now I have the polymer from it. So if they ask you to make the repeat unit, this is how you do it. Any questions? Quick question. You can ask your question if you have it. But my question is, what would you call this? What would be the name of this molecule, Nietzsche? Well, you have to realize that this is propene. So this would be polypropene. Yeah. How would you define polymerization? Well, it's a good question. I don't know the exact words for it. Maybe let me come back to you. But essentially, I guess an alkene that breaks open its bond, double bond, and starts, adding itself to form a larger molecule, or maybe just smaller monomers joined together of an alkene joined together to form a larger molecule. Somewhere in that approximation, I can get a better definition for you. But yeah. Okay. So polymerization is less about the chemistry, more about technically how do these atoms break up? What do you mean? All right, people, half the questions you guys ask, I don't understand it. Because how do these atoms break up? Atoms don't break up, right? Molecules break up. So Salman, you're making a mistake, but I don't understand what you're saying. We're not even breaking it up. We're joining them together. So are you asking why the double bond breaks? How does it become CH3? Huh? I still don't get it. How do they? Do you want to turn on your mic and ask the question?
Am I audible?
You're audible, yeah.
Sir, so C in propene, so C and H, how do they become CH3 in the next after they become polymers?
Because it's already a CH3 to begin with, no? In the monomer, the CH3 is already present. So this part is already part of what we were talking about. Right? This molecule, I redrew it like this so I could write it down easily, just for my convenience. If I tried to polymerize, ये तो अजीब कुछ जंगली सी चीज बन जाएगी ना. I don't really want to polymerize this, right? So I took this and I wrote this as CH3 so that I could easily make a mono or polymer out of it. यहाँ से bond खोले and essentially I made a repeat unit. And this over here is the same thing over here without the double bond present, and it's opened up like that. And this is called a repeat unit. At least this part of the molecule is a repeat unit. And now what I'm doing is just copy pasting this. So instead of copy pasting, you just redraw it. Does that make sense, Salman? Yeah, I hope it did. So over here, some terminology. is, this is propene, this is called a monomer, जिससे आपका polymer बनता है, monomer. To make a monomer, you first need to figure out a repeat unit. For it, essentially, you open it up at the double bond. I mean, you don't have to, but it makes your life easier if you're ever confused. This is called a repeat unit, meaning this is the part that keeps on repeating over and over again. So if you get what have I done? I took away the carbon-carbon double bond, opened it up like that. So the bond was here, it broke from here. Now it's opened up like that. So this part I'll just copy and paste over and over again multiple times, at least 3 times for the examiner to show a polymer. So I'll copy this from here. Next time I'll just go live on YouTube. This is known as a polymer. But another way of representing a polymer is making a repeat unit and putting 2 brackets on it. And writing an N over here. This means the same thing, meaning this is a repeat unit that keeps on repeating. Your polymer, what you're talking about is this just repeated N times. So they do it like this. One important thing they really like to ask you guys to do is make the bonds a little longer and make sure the bracket you're drawing cuts these bonds. This is important to do. So let me just highlight that. This is V important, very important. Okay, something you really have to do. Yeah. All right, third one. What was the color code I was using? Oh, fourth one. Did I miscount or are we on fourth one? Fourth one is bromination. Probably the easiest out of all of them. Yeah, man. Okay. Bromination is it reacts with bromine readily. I'm sure you guys have heard of the word readily before. It just means without any conditions, it'll just readily react. Right? This is what happens. Now, alkanes and alkenes and alcohols, all your organic molecules are known to be absolutely colorless. Bromine is very distinctly orange in color. And any product, most products, if not all of them, for organic molecules are colorless. So this is also colorless. So what ends up happening is, what you end up seeing is, if you mix bromine gas, well, is it similar to the reduction of alkenes? I guess you can call it, you could call this an addition reaction if you want, but it's just, again, incorrect to call it addition. Is it similar? I guess, but you can say hydration is also similar, right? Because essentially the bond breaks up, opens up, and something gets attached here, something else gets attached here. Why am I writing HCl? Something gets attached here, something gets attached here. Aside from polymerization, all alkene reactions are this essentially, right? So yeah, if you want to call it that, sure. So this is a very interesting test because it's a little famous. Not just because how it can happen, it's famous because it's a very distinct color change. What happens is, if you have a gaseous chamber, let's say this is a column, and you have bromine inside, so gas, right? So it's going to be orange in color, and let's say you could input somehow, there's no input over here, way of putting in a gas, but if you could, let's say you put any alkene in there, what's going to happen is the alkene will react with the bromine to form a bromoalkane. This is called a bromoalkane. It's just the name, right? And the product will be colorless. So what you'll see is the entire orange color disappears. So this is such a visual reaction that you use it to test for alkenes. I mean, you can use another reaction, do it, but anything else you use might be a little tricky. For one thing, let's say you wanted to use hydrogen. Well, hydrogen is also colorless and the product is also colorless. So how would you know? Maybe you can test for it somehow, but you're just making your life complicated. Over here, a quick color change quickly tells you that the reaction has taken place. And whatever this unknown colorless gas was definitely an alkene, because the carbon-carbon double bond has to be present. That is what the bromine likes to attack. Does that make sense to everyone? Another good thing about this is this reaction just happens at RTP. So no conditions are required. You can see petrol, but you can also see water with that description, Salman. It has like a these chemicals, like they're colorless, they don't have a color, but water doesn't have color either, but you can see water. Why? Because anything it touches, it makes it look darker, right? If your clothes are wet, it's because they look darker than when they are dry. So water does that. The other thing water does is it bends light. So every time you see water is gonna create an optical illusion, right? It bends light, so everything in water looks weird, like a lens, right? So you're like, oh, it does what glass does, so it has to be water over there, right? So petrol has a slight tinge of being, slightly yellowish, I think that's what I've seen, but practically to the, like it's negligible. It's not a distinct color, but I think it is a slightly yellowish, ever so slightly yellowish color. So if you have water on one side, petrol on the other side, you can distinguish between the two. But, it's hard to say. It's ever so slightly yellow in color. Who would believe you? It's hard to comment on that. Anyway, I think this made sense to everyone. Thumbs up if you guys get it. Thumbs down if you don't get it. Pretty easy, pretty straightforward. Okay. Oh, I think one reaction we missed, which was cracking. So let's do that. All right. Let me go back and mention cracking. I want to talk about cracking. I'll do it for alkanes because you can do it for anything, but mostly they'll deal with alkanes. So this is chlorine in sunlight. I'll do it before chlorine because this reaction is only for alkanes. Yet alkenes and other molecules can undergo this reaction. But yeah. Cracking. Cracking is pretty silly. It's pretty straightforward. Cracking is essentially when you have a larger hydrocarbon, let's say, C20 plus, no, what am I saying? C20H22, it's an alkane I'm using, and you can force it to break down into smaller components. Generally, you'll see two components show up. So this could happen anywhere. Randomly, it can break down. But normally what you'll see is they'll show you one particular equation. Let's go with 10H24, right? Now, if this is an alkane on the left-hand side, this is an alkane, and it breaks down to form another alkane, smaller one. But let's say it breaks down exactly into two products. It can do it in multiple times. It's not consistent. But let's say the other carbon, it only breaks down into exact two molecules, right? So one is this one. The other one has to have how many? You start with 20 and you're only making two molecules. So the first one has 10, so the other one has to have the rest of the number of carbons, right? So the other 10, right? Because 10 plus 10 is 20 now, right? So you get C10, but how many hydrogens are you left with? I think I made a mistake again. This has to be 22 because CN H2N plus 2, right? That's an alkane. Now, how many hydrogens are you left with? Well, you had 22, and now you, what am I saying? Not having a good day. 42. Let me start over. You have C20H42, which breaks down into C10H22 and C10 blank, right? This is the part where examiner really like to tease you with questions, but it's basic math. The idea is, if you can never produce two alkanes. Why? Is because to have an alkane, you should have 2n plus 2 number of hydrogens. So if I put another 2n plus 2 over here, that would be 22 again. I hope the number's correct this time, because I'm not really bothering to count it. If it's 22 and 22, the total number of hydrogens are 44 hydrogens. You don't have 44 to begin with. So it cannot make another alkane. So what it ends up doing is the second molecule produced is always an alkene. Right? I think I fixed it. Right? And this is essentially it. Because they'll give you a question like this. Let me just erase this for a second. Let's say C20H42 undergoes cracking and produces C10H22 in X. What could X be? And what you have to realize is I just subtract 10 from here and this number from this number, 42. So you're left with something which we saw, C10H, what is it, 20, yeah. And you have to realize that this is absolutely an alkene. Now, people find this confusing because why would this be like, why is it doing it like this? Can it make more? Can it break down into 3 products? Can it break down into 4, 5? There's no end to it. Kind of like the chlorine example we saw. Where is it? This one, there's no limit to it. Well, your limit is the number of carbons. But if this was like C4H10, this would be a lot more products, right? So if I go back over here, there would be no limit for this. Multiple, it could break down into multiple. But generally for O levels, they'll deal with like 2 products formed because they want to ask questions which are math related, not cracking or chemistry related, because it's condescending, honestly. They'll give you 2, and you have to realize essentially if you're forming one alkane, the other one has to be an alkene. Just because you don't have enough hydrogens. And that's it. Because people are generally confused for cracking, not because how to do it, but like how little people talk about it. It's actually not because, it's actually that cracking is very random. No one tells cracking, कि भाई मुझे 10 carbon equally divide कर दो. It'll randomly do it. But what is this equation for? Let's say one particular molecule of C20H42 broke up like this. Can we talk about it now? And that's how the questions are organized. Not that if you throw C20H42 into a chamber, into a vat or something, will all the molecules be produced will be exactly these? No, you can't control what's going on, much like you can't control what's being produced, right? That's the point. But once these are produced, you can separate them by fractional distillation or any other method you've seen. That seems good to you, right? But that's essentially what cracking is. Now, cracking is underdone in two ways. One is through steam. The other is catalytic cracking. You use a catalyst. Means for steam, you'll use water, right? The catalyst used is Al2O3, aluminum oxide. Now, this is a popular chemical. It's very abundant, especially in clay. So what you'll see is normally in exam questions, instead of writing down aluminum oxide, they'll write down clay pots or shards of broken clay. Yeah, that's better. Shards of clay pots. What they do is, like a broken clay pot, they'll take the, mitti ke jo hota hai na, where you put pots, and literally that, they pick it up and they throw it in a test tube, and yeah, they pass an alkane over it by heating it, and it prevents it from, it encourages the reaction and cracks it down. ठीक है. Pretty easy. I'll move on. We're left with alcohols, and we'll take a quick break once we're done with alcohols and acids, and I'll do it pretty fast. Alcohols don't really have a reaction. Alcohols. For alcohols, you can produce ethanol from a biological sort of like a chemical reaction, I guess. It is called fermentation. So essentially, how does fermentation happen? Is any sugar molecules present sugar molecules, molecular formula is C6H12O6, and they introduce bacteria to it or yeast to it, right? Which breaks it down to form a particular alcohol, not any alcohol, C2H5OH plus carbon dioxide. It's not balanced. One interesting thing about this is it is an exothermic reaction, so enthalpy change is negative. Yeah. Now, you can only make ethanol from this. Nothing else. And if you're wondering in real life, where is this reaction taking place? This is essentially how drinking alcohol is made. Ethanol is the beverage we have, ethanol. Okay. This is how it's made. So essentially, you take fruits, vegetables, or anything, and you can keep it with yeast, and you keep it in a oxygen proof, oxygen logged chamber. I mean, the fruit doesn't have to be rotten. Like you can take fresh ones. I don't know actually what they do with it. But to make alcohol, like if you've seen a documentary with it, like, there's a famous documentary, Discovery Channel key, where like they make champagne and they do like 28 different things to it. Most of the things they're trying to do is to give alcohol, because it's a drink, right? They have to give it its characteristic taste, what people like to drink, right? So they do it a particular way. Maybe they rot the fruit first or something like that. But if you have the correct yeast, you can just literally, I don't know if you can throw sugar in it, but you can throw any food with high sugar in it and it'll just produce it. So alcohol can be made from anything. Like I've seen enough anime to know sake, the Japanese people, what they call alcohol is primarily made from rice, because rice is very abundant. In Russia, they have vodka, and vodka is known to be made from potatoes, I think, vodka or whiskey, something like that. Champagne is a special place in France where they use special grapes that only grow in one village in France. I think something like that. And wine is from grapes, and you can go on, right? I think beer is from wheat, right? Like gandum, the atta jisse banta hai. So you can use a wide variety of vegetables to produce your alcohol. Okay. So one popular use of alcohol, let's pause the chemistry for a bit because this ethanol is pretty important. Why? Because people like to drink it. The other thing why it's pretty famous is, I think it's very easy to make. The other reason is it is a good source of energy. It's a good fuel source. So in countries like Brazil, where there's a lot of sugarcane, even it should be the case in Pakistan, but it's not. But in countries like Brazil, or some country, I can't remember the country properly, they have a lot of sugarcane and they use the sugarcane to produce ethanol. And you can't produce 100% ethanol from this because ethanol is a disinfectant. It'll kill the yeast. But once you produce enough, you can distill it out and get pure ethanol. They use it to fuel their cars. Literally, how we use petrol, they have ethanol, they put it in the cars and it burns really well. And they use it to drive. So it's a biofuel. Right? So this is why this fermentation reaction is popular, because not because it's a famous reaction or anything, it's just widely used in the industry to produce drinking alcohol and as a fuel source. And ethanol's other uses are it's a good disinfectant. Like I'm sure you've seen like soldiers get shot in a war and they'll take out a bottle of whiskey and they'll throw it on their wound and they'll scream and whatever, but they're just trying to not get infected because, yeah, it's a good disinfectant. I don't know if I'd recommend that. I don't know if that's a good idea or not, but that's Hollywood for you. I don't know. Yes, the alcohol produced, Salman, is extremely diluted. It's like, I think after 15%, you can get a concentrated version because ethanol at that concentration kills the yeast. Then what they do is they'll fractionally distillate and extract all the ethanol, and then you have 100% of that alcohol. And they use that for, whatever they want to use. Okay, pretty good. Another reaction for alcohols is oxidation of alcohols. Oxidation of alcohol. So this is only true for ethanol, right? This is the important part. But over here, this is true for all alcohols. So let me write that down over here, only for ethanol. How would you produce ethanol otherwise? You take ethene and react it with water, with phosphoric acid, which we saw earlier, if you don't want to ferment it. Only for ethanol. Okay, oxidation. alcohols, any alcohol, I'm drawing ethanol again, because that's a famous alcohol, I guess. But any alcohol can be readily oxidized to its counterpart acid. By counterpart, I mean they have the same number of carbons. Where there was an OH, there is now, the OH is still there, but the same carbon has an oxygen and has lost all the hydrogens. You don't have to balance this equation out. You don't really have to know it. One thing you might see in exam questions or anywhere else is this sort of oxygen shows up. This means an oxygen somewhere is reacting, and this is an oxidizing oxygen, meaning some oxidizing agent you put in there is giving you this, right? This oxygen, which is being used to oxidize it. So it's a replacement for writing the full equation, which we're skipping. We're not writing it. We don't need for it. There's no need for it, but we're just showing that it can readily oxidize. What is the reagent for this? It is acidified potassium manganate, KMnO4, the reducing agent you knew from your redox chapter, KMnO4. You can use it to produce ethanoic acid. And what else do you need for it? Heat. And a lot of people will say heat it under reflux. There's a reflux is essentially a tube on top of a round bottom flask, kind of like that. And what they do is they pass cold water in there. I'm really going to butcher this drawing. So when because you have to heat it, what could happen is the ethanol can evaporate. So what you want the ethanol that goes up, this cools it down and throws the ethanol back in. So heat under reflux. Sometimes you'll see it. A lot of people like talking about it because it's more of an A-level thing. But if you don't know, just put a big bracket around it and ignore it, because O-levels doesn't really emphasize it. But I don't want people to get confused because हमारे teacher ने तो ये पढ़ाया था, heat under reflux. ठीक है. If you've seen a few movies, you probably have seen that, oh, the alcohol turns sour. Like, you know, wine is turning sour. Why is that? Alcohol, maybe it has a lot of chemicals in it, can end up turning into, this alcohol can oxidize and end up turning into ethanoic acid, which is C2, no, it's CH3, COOH. Ethanoic acid is vinegar. So a lot of people say, oh, alcohol is sour or whatever. And yeah, you produce vinegar from ethanol, right? You can do it just by the same process, but to produce alcohol, you lock out the oxygen. But if you introduce oxygen to this, this will turn into vinegar instead of wine or alcohol. Isn't it easily flammable? That's why people put perfumes on cuts. Yeah, true. Isn't it easily flammable? Yeah. If you don't do this, but if you light a match or a lighter and spray on top of it, it'll like dhamaka ho jayega. Even a lot of people, what they do is they light a lighter and they spray either alcohol. You've probably seen people spray like muh mein alcohol rakh lete and they blow onto it and it just creates like a big flame just to look cool, I guess. Very dangerous, don't do it. And please don't do it. And what they do is like deodorant cans also, very flammable. Yeah, very Game of Thrones. Let's end it here. I think we're exceeding the time. I'm kind of exhausted as well. Do people have questions right now? Oh, I think I want to do acids as well. So let's finish it up by putting in carboxylic acids. Carboxylic acid essentially one of the reactions you've already done, which is oxidation of ethanol. So I won't write it again. C, alcohol. Right? But we'll move on to the second one, which is called esterification. Esterification. What is esterification? This will probably be the time where you realize, oh, I should have really learned how to draw or appreciate the drawing in order, because now it's going to get tricky from now. Here you have ethanoic acid, and on the other side, you have an alcohol. I'll draw the alcohol in reverse because you'll see what I mean. It's the same ethanol we've seen so far, but now it's drawn in reverse. And there's no room to draw it over here, so I won't do that here, but I'll just do it a little niche. Essentially what happens is, now this is a key part. The OH from the acid breaks apart, and the hydrogen from the alcohol break apart, and you have an OH and an H, they form H2O. It breaks apart and they form H2O. Once this happens, you're left with an acid without a bond. And an alcohol without a bond. So what ends up happening is they join in this area to form an ester. This is known as an ester. This weird looking molecule is an ester. And this part is the important part. Like literally you want to zone out this entire part of the molecule and this entire part of the molecule. This is the focus anytime. This is called an ester link. Because this is where the link is formed, and this is called an ester. So this is where the ester is formed. And that's an ester. There are conditions for this are concentrated sulfuric acid. And of course, the ingredients and heat. Right? Now, this is pretty important. And one of the more important parts are two things. Well, ester link. The other important part is the OH gets removed from the acid, the H gets removed from the alcohol. I don't care what anyone else is saying, this is what happens. And this is very important because the next chapter is polymerization, which deals primarily in this. If you don't understand this properly, or if you forget, that entire chapter can go. How would you name this ester? We're not talking about naming right now, but we can talk about it later. I'm pretty tired, so we'll continue this a little later. Does that make sense? I'll let you know. I'll let you guys know when the next class is. And yeah, chalo. TTYL, thanks for coming in. If you have any questions, you can drop a message on my DMs and Facebook. And yeah, let's end it here. No problem, guys. Take care. Bye-bye.